everybody. My name's James Thomas, and I'm a developer advocate at IBM Cloud. I'm also the lead serverless advocate for IBM, which is a really fun job. And today I'm going to be talking about this. Where am I? So what I should be talking about is, all right, serverless machine learning with TensorFlow.js. Ta-da! How to use these technologies, serverless machine learning with TensorFlow.js to build kind of real-time scalable machine learning pipelines in the cloud. And I've actually used these technologies recently, serverless machine learning, TensorFlow.js, to build myself an application to fix a problem I was having at work. So I'm going to talk about that application, talk about some of the kind of many challenges that I overcome having to kind of build it and give you the skills to go away and do this kind of stuff yourself. So I said I used these technologies recently, right? Serverless and TensorFlow to build myself fix a problem I was having at work. What was the problem I was having? Well, I'm a developer advocate, so I spend a lot of my time on stage doing stuff like this, talking to developers about serverless, trying to get them excited. And when I come home from my trips, as I will do tomorrow, I have to write a trip report, right? Kind of talk about how the trip went and any feedback I have and that kind of stuff, things I learned to justify all the expenses I'm kind of racking up traveling around. And one of the things I like to do or to put in my trip reports is if I find any tweets about me on social media, when people are taking photos, I normally put that in there because I think if you're tweeting about a talk, it means you had a good time and kind of feed that up to my bosses and make them happy. Hint, hint. So the problem is that, unlike this gentleman who's been very good, not everyone always tags you in the photos, hint, hint. You know, they often just put photos up randomly, right? And I still like to kind of find these for the conference. And the only way many times to find these photos of you at events is to go to Twitter search, put in the conference hashtag, and just keep scrolling to the bottom of the page and just manually trawling through all of those photos. And this is very boring. This is incredibly boring, and I didn't want to do this anymore, given that I go to like 20+ events a year. So when I normally have some kind of boring task to do at work, my normal thought is, can't I write some code to do this for me? Can I kind of automate this task out of existence? And this didn't seem like too much of an outrageous idea. Right? Twitter has an API. We can kind of get tweets programmatically. And I thought, can't I use some kind of magic machine learning AI cognitive service in the cloud to look at the photos and tell me if I'm in them, right? And if I'm in them, then it can just tell me and I can include it in my trip report. Now, for me, the obvious challenge here was that I don't have any skills in machine learning. I'm not a machine learning engineer. I'm not a data scientist. I don't really know any of the libraries or toolkits. And I can't remember linear algebra, all of that kind of stuff. But it seemed like something that was maybe possible. So I wanted to give it a go, hack around for a couple of weeks, and see what I could come up with. And the kind of the tools I wanted to use were JavaScript, serverless cloud platforms, and NPM, right? Anything I could find on the wonderful world of NPM libraries. So I kind of spent a couple of weeks hacking around, and to my own amazement, after a couple of weeks, I'd built myself this app called Find Me that allowed me to do just that. Allowed me to find unlabeled pictures of me on social media using serverless cloud platforms and using serverless or using machine learning. I'm going to show you a quick demo now. I'm going to show a video because I don't trust conference Wi-Fi. So I went to this conference in the summer. I helped organize it, called Serverless Days London. There was lots of content about it on social media. And because I was an organizer, I know that I'm in a lot of these photos somewhere because I was on stage introducing people. I was always kind of in the background. But there's loads of photos of me somewhere, but many of them aren't labeled. So using my app, Find Me, you can go and take the conference hashtag. You can dump it in there. You'd log in with Auth0, so I have access to your Twitter account. And you put in the hashtag, and it will send a message to the serverless backend to go and start searching for any tweets about that conference using the API. It finds 180 tweets, 130 tweets, 129 with 84 images, and then it fires a message off to a serverless function to process all of those images in parallel to do face detection, and then looks at my profile image and tries to find me, and if it does, it tells the front end and renders it to the screen. So there you can go. There's some tweets with me, there's some tweets me again, but I'm not tagged in any of these tweets, right? It doesn't use my name or my user account. It's found me using machine learning, using the serverless backend. And what I find kind of more amazing about this is how accurate the machine learning is. You see in many of these photos, I'm not looking, it's not like a profile picture of me. I'm just kind of looking at the stage or looking at the floor in the background, and it's managed to pick me up, which is pretty amazing. Out of 84 images, it's found 5 unlabeled images of me. So let's start by actually having a look at the architecture of this application. And this is what it looks like at a high level. So it's actually a relatively simple serverless application. It's only got 4 serverless functions, 2 API handlers and 2 kind of back-end services. And it's only 550 lines of JavaScript, right? It's a tiny amount of code to do something I actually think is quite a complex app. And how it works is this, right? You go to the client-side web page, you click a button to search. It sends an API request to the API handler, which registers a search job in the backend. It asynchronously invokes the Twitter search function, which goes and talks to the Twitter API and sees if it can retrieve any tweets for your conference. And then for any tweets that come back, if they have an image, it processes them all in parallel. So it has another serverless function which gets invoked asynchronously and uses machine learning to process all those images, and it takes your Twitter profile, so it uses my profile image, and the tweet photo, it does face extraction, and then compares them, and if it finds any matches, it writes them into Redis that it can kind of stream back to the UI as well. Now, what I find most interesting about this architecture is that it turns out it suits serverless really, really well, because this particular application, most of the time, I'm not using it, right? I only use it when I come back from conferences and things like that. So with serverless, you don't pay for idle, right? So there's no charge for me for running this app, except when I actually tried to use it, which is very nice. And then when I want to use it and I want to click search, it's going to actually use the power of serverless to make it really, really fast, because I can scale up really, really quickly and process all of those images in parallel and get the results in real time. So using serverless, it works really well because no charge for idle, and then when I need to scale, I can scale almost immediately. And this is all built on IBM Cloud Functions, which is based on a really nice open source serverless platform called Apache OpenWhisk. So if you like Cloud Functions, you like OpenWhisk, go check it out. But to me, the most interesting thing about this architecture is the face recognition function. This is just a normal JavaScript function, right, running in a serverless runtime. So which means it doesn't have access to a GPU, doesn't have dedicated hardware, any of that kind of stuff. And also, it doesn't call any external machine learning service. It's not calling Watson visual recognition or anything like that. All of the machine learning is done in the JavaScript runtime using this library called TensorFlow.js. So TensorFlow.js is Google's official JavaScript version of the TensorFlow library that they announced this year on March 30th. And originally when it came out, it was very much targeting the browser. So it's a browser-based library that you would include, and you could do stuff with the webcam and images on the page and all this kind of stuff. And they'd also done lots of work to make it easy to use for non-data scientists, which is me, by pre-training models and the utilities and libraries and all of that kind of stuff. And although originally it came out and it was very much focused on the browser, about 2 months later they announced a Node.js driver. So this was the ability to use that JavaScript library in Node.js with an NPM library that could access the GPU or the CPU natively using a shared library. And this meant that you could use TensorFlow.js in any JavaScript runtime, any Node runtime, including serverless cloud platforms. Now, the great thing about JavaScript libraries is that people build libraries on top of them. And I actually found this library called faceAPI.js. So this gives you a high-level JavaScript API for doing face detection and face recognition in images using a pre-trained model, no training needed, and it builds on top of TensorFlow.js. So you don't have to use TensorFlow directly or JS, you use this higher-level library. And this is what I actually used in my serverless runtime for doing that face detection and face extraction. So if you're listening to me, right, you're thinking, cool, right, we've got all these awesome JavaScript libraries for doing machine learning, we can use them on serverless runtimes. You might be thinking, like, is this the end of the talk, right? I'm just going to create a new serverless project, I'm going to npm install those libraries, and I'm going to write some code, and we're going to deploy, right? What else is there to kind of learn? Well, if you think this, as I naively did when I started my project, I'm going to say not so fast, right, which is a bit of a kind of serverless joke, because, some of you laughing, because like serverless runtimes are not like normal Node.js environments, and there's a lot of challenges to getting libraries, especially libraries around machine learning, working in them. And I ran into lots and lots of challenges. So I'm going to talk about many of the challenges I ran into and had to overcome so you can go away and do this kind of stuff yourself. Now, when you're building a serverless application, or maybe any application, I think this is a really good approach to follow, right? Make it work, make it right, make it fast, right? In the beginning, for me at least, this is the steps I followed where I just wanted to get my application working. I wanted to get an end-to-end demo and validate that it could actually do what I wanted it to. And then I was going to try it with more realistic test data, see if it would kind of work at speed. And then finally, I wanted to optimize it. I wanted to make it as fast as possible because with serverless, time is literally money. The faster your application runs, the less milliseconds it uses, the less your cloud bill is going to be from your provider at the end of the month. And I'm going to walk through the challenges in this kind of order, right? You know, getting it working, making it right, and then doing the performance optimization at the end. So let's go back to the first challenge, right? I said if you just create a new serverless project and you npm install that library and you try and deploy, you're going to get this error back from your serverless provider, right? Deployment package too large, like, oh dear, what's going on? So with serverless cloud platforms, you're normally limited if you're uploading a zip file. Most of them limit you to around 48 megabytes, some a little bit larger, but a relatively small amount for all your libraries and dependencies and code to instantiate on the platform. And this is something we kind of run into. So it turns out that just installing that one npm module leaves you with a deployment package that is too large. So I went kind of digging around, and I discovered, again, just installing that one npm module gave me a node modules of 1/4 gigabyte, which even for JavaScript land is pretty big, right? And I was like, OK, this is fine. We sometimes encounter this. I'll use Webpack or something. And I started to dig through the files again to see what was going on. And it turns out the reason this is so big is that the TensorFlow.js node driver compiles a native library, libtensorflow.so, which is 142 megabytes, right? It turns out it uses a native library to access the GPU and the CPU, and this is just very big, right? It's 142 megabytes. And because it's not JavaScript, I can't use Webpack to compress it down or something like that. So it seemed like a bit of a difficult problem. Now, if you've been doing serverless for a while, as I have, you've kind of come across this kind of problem before. And the normal, slightly hacky workaround is something like this. You have some kind of code, initialization code in your function, which will you store big libraries, external dependencies on object store. And then basically, during cold starts, you just pull them in and you write them to the file system, and kind of away you go, right? It's a bit slow. It's not a great approach, but it's often what you do. However, because I'm using IBM Cloud Functions, which is based on an open source project called Apache OpenWhisk, one of the nice features that OpenWhisk has for doing serverless is that as well as pushing your code up to the platform, you can also give it a custom Docker image to use as a custom runtime. So what I can do is build myself a custom TensorFlow.js runtime, extending the existing images and just pre-install that library so I don't need to include it in the deployment package. OpenWhisk publishes pretty much all of the existing base images on Docker Hub, right? So you can just go and you can pull one of those down. And if you want to build a new runtime, all you have to do is use the existing image as the base image, and then you just npm install any dependencies that you want. You build it, you push it back to Docker Hub, and then you can use it in your serverless project configuration. So where I've configured my function down here, my JavaScript handler, I just give a reference to that public Docker image. And OpenWhisk will pull that in and use it as a custom runtime, which will have those libraries pre-installed, which means I don't need to install them locally and include them in my deployment package, which means my deployment package is going to be much, much smaller. It's going to get under that limit. So this is how I solved the first problem, right? I needed the library in the platform. It was too big to deploy. I just built a custom runtime. The next thing you're going to need to do is load the TensorFlow.js model files. Now, the model file is obviously what actually does that you can use for classification. It's going to be used with libraries and things like that. And the model files come in two kind of flavors. They have a JSON configuration file, kind of top-level config file, which contains all the nodes and the connections between them, and kind of is a high-level meta overview of the model. And then you have these binary weighted shard files. So there's all the binary weights of the model, and the model weights are like the secret source, right? It's the thing that actually does the classification. And so it splits these relatively large model weights into separate binary files you need to download and install. Now, rather than you having to deal with these files manually, which is kind of slightly messy, the TensorFlow.js library has this high-level utility called TensorFlow Models, which will load pre-trained models from the internet asynchronously using HTTP. So rather than you having to work out what version of the model and what file and the JSON and all that kind of stuff, you can just do these 2 lines of code to load the model. And you'll see this example all over the place in the docs. Now, if you try and take this code and run it in a serverless runtime or any node environment, you're going to get an error thrown back, which is fetch is not defined. So what's going on? Why does this occur? And this kind of error crept up again and again when I was kind of playing with this stuff. And the reason this occurs because although TensorFlow.js has a Node.js driver, many of these high-level libraries and utilities haven't been converted over to fully work in the Node runtime. So for example, this was still expecting to run in a browser and use fetch, which is the HTTP client, to access those model files. And in Node.js, the runtime doesn't have a fetch library built in. Now, because I was still in, I call this the get it working phase, right? My solution was just to stub out an implementation of the fetch library. So if you go to npm, you can download node fetch, which is a Node.js version of that fetch library. You can put it as a global variable, and then that error is going to go away, right? We're going to look at a way to optimize that in the future, but that was a really, really easy solution just to get around this in my kind of get it working stage. And once you've actually got the models loading, the next thing you want to do is do classifications. You want to do predictions. You want to give it, in my case, I want to give it an image, and I want to get back some faces or some classifications that come back. And again, if you go and look in the documentation, this is the kind of stuff you see for TensorFlow.js. This snippet is all over the place where they say, yeah, document element by ID, model.classify. But the obvious problem here is that I'm not running in a browser, right? I don't have a document. I don't have, a DOM and all this kind of stuff. And the strategy I used last time of stubbing out libraries and things like that is not really scalable. I'm not going to stub out a whole browser environment to just pass it an image. I want to pass an image from a file system, right? Not from some element on a page. So this was a bit more tricky, and this wasn't really documented about what you're supposed to do at this point. And lots of people ask about this in the forum. So I spent a lot of time reading the TypeScript code and just reading the docs and kind of scratching my head at this point. And eventually I figured it out. So if you look at the docs, you'll see that in the model.classify method, you can pass in like an image, a canvas, a video element, all this kind of stuff. Or you can pass in this thing called a TF tensor. And it turns out if you pass an image to the model to classify, all the library does under the covers is take the image data and convert it into this TF tensor. And you can manually create these input tensors, as they're called, and pass it into the model for classification. And a tensor, an input tensor, is essentially, think of it as an array of values. It's just an array of values of the data to pass into the model, and it has some metadata about the dimensionality of the data and also the type of values you're passing in, integers, bools, floats, all of that kind of stuff. So what I'm going to do is I'm going to create an input tensor manually from my image on the file system. But what is the data that I need to pass to the constructor for the TF tensor? Like if I've got an image on the file system, what are the values that we're going to use for classification? Well, if we take this picture of Doug the Pug, which is a very popular dog with its Instagram account, all images can be translated into a series of essentially RGB values. So if you take the RGB values for every pixel and just string them together, that is what you're going to pass into that mobile net model for classification. Once those RGB values concatenated together. So how do you get the RGB values for a file in Node from your file system? It's pretty easy. I just went to npm and found this library called jpeg-js. And you can read the file from the file system. And this library has this method called jpeg.decode. And it gives you back some metadata about the image, the width and the height. But then this data field, which is an array of those RGB values, which is exactly what we want to pass into the model for classification. Now, a little pro tip here, you need to ignore the alpha channel. So it turns out that certain JPEG formats have an alpha channel for transparency, and so that library will always give you back 4 values for every pixel, RGB and A, and you don't want the alpha channel. The model doesn't use it, so you just need to strip those out before you pass it for classification. The easiest way to do this is called data.filter, getting rid of all those 4th index values, which is an easy way to remove the alpha channels, and then you just have the RGB that you can use. Now you have the I had the RGB values, I could finally construct my input tensor. And the next 3 lines of code is going to be a little bit more complicated, but this is as low level as I had to go to get this kind of thing working. This is about as much as I need to know about the underlying TensorFlow library. So all you have to do is you have to create a new typed array of the right format with your RGB values, construct the shape, which is just the width and the height and the number of pixel values, and then you can call the TF tensor constructor with those values in the shape and the type of data, and then you can pass that input tensor to the model for classification. And this is all I kind of had to do to get images being read from the file system. Now again, if you go in the community forum for TensorFlow.js, people ask how to do this all the time. It's not really documented anywhere, but this is how I use it. You can use this approach with any library pretty much that builds on TensorFlow. They all allow you to basically construct the input tensor manually and pass it through to the model for classification. So at this phase, I kind of actually validated my assumptions. I'd kind of made it work. I got a very crude end-to-end demo working, and it looks that maybe this thing was actually going to work. And so the next thing to do was to make it right, to try it with more realistic test data, to kind of push on it and try and flesh out any bugs. And really quickly, a really interesting bug started to occur. And the bug was this, right? I would invoke my serverless function, my kind of demo classification function with some input data, and it would just work, right? It would return me the results. I'd invoke it again, it would work again. I'd invoke it a third time, and it would work. And then it would die with an out-of-memory exception, right? Oh dear. And if I did it again, it would go through this pattern, right? It was always the fourth one that died. So what was going on, right? I had a memory leak, but I kind of looked through the JavaScript code, and I was like, memory leaks? Like, really? And it turns out it was on this line. So when you create your input tensors, so when you're working with TensorFlow and you're passing values in to create the tensors which then go to the model, those values get passed directly through to the native library and stored for access on the CPU and the GPU, which means that they don't get garbage collected by the Node.js runtime. So every time I was invoking that function, it was passing an image, a whole megabyte of image through to the native library. That was allocating more memory, and then more memory, and eventually on the fourth one, it just died. Now, this is actually my fault. This is expected behavior, and I just hadn't read the TensorFlow docs very carefully, because they have this dispose method that you can call on your input tensors after classification to basically release the native memory and make this easy to do. So this, once I kind of actually done some more reading, this was relatively easy to fix. I just need to have input.dispose at the end, and then I wasn't getting any memory leaks anymore. And that was pretty much it. That was in the make it right stage. That memory leak was about the only thing I encountered that kind of gave me some difficulty. Serverless just works. TensorFlow just works. It was working really well. And so I moved on to the final stage, which was make it fast. Serverless time is literally money with serverless. The quicker your functions run, the less you get charged. So you've got a very direct economic incentive to make them very, very fast. And whenever you're doing any kind of performance analysis, you need to start from a baseline. When I started doing some measurements, this was my baseline performance, right? What we call cold invocations, around 8 seconds for classification, and warm was around 5 seconds. And I actually thought, I was kind of impressed by this. I thought this is pretty good out of the gate for a little serverless runtime with like half a gig of RAM. It works fairly well, but I thought I'd not done any performance stuff. Let's see how far we can get it and how fast I can make it. Because I wanted the results to be real time. I wanted to click that button and see results as fast as possible, not come back in 10 minutes. And the performance you saw in the video was what it really looks like. So I added some kind of console.time statements to the code, and it turns out that most of the time in the function, the classification function, was spent in these 5 main sections. So there was an initialization delay with cold starts where it was loading the libraries and instantiating everything. It was around 1,200 milliseconds. Obviously, it doesn't occur with warm invocations. There was model loading. So it turns out that this was particularly computationally intensive. Loading all those model files, just instantiating them in JavaScript was particularly intensive. It was around 2 or 3 seconds. Then there was the image loading and face detection. And actually, what I need to do is, when I called the function, I called it with your Twitter profile image and the image for the tweets, right? And it had to take those, had to convert both those images to input tensors, then run face recognition against them, and any faces that come back, it would compare and see if there was any matches. And that took 500 milliseconds, 700 to 900 milliseconds, and it did that process twice for each image. And then there was some other time, which I wasn't really sure where it went, so I've just put it as everything else. So the first thing to say is, OK, so the most obvious place to start optimizing is the model loading, right? Because that's where it's spending the most amount of time. And my initial thought was, OK, well, the model files are being loaded from the internet every time. So what if I just have them available locally and it doesn't have to read from the internet? Surely that has to be faster. And there was a really easy way to do this because I was already building a custom Docker runtime for my serverless functions on OpenWhisk. So all I had to do is download the model weights that were being used locally, add them into the Docker file or into the Docker build, and then they would be available on the file system, right? They're going to be on the file system, not the HTTP interface, and that should be much quicker. Now, the challenge here was, yeah, but the library uses a HTTP client to talk to the internet to fetch them. Like, how can I make them read it for the file system? And my terrible or genius workaround for this was to write my own version of a HTTP client that proxied to fs.readsync file sync. So this is the whole thing. I need to implement 2 lines, right? JSON and array buffer, and it just worked magically. So that was pretty good. But it turns out this didn't make as much of an improvement as I thought. It only shaved off around 500 milliseconds from the model loading. Turns out just instantiating 30 or 40 megabytes worth of model files in the runtime is just kind of computationally intensive. So I started to think a bit more about how we could optimize this further. And a good approach, if you're building serverless, right, regardless of what you're doing with it, a good approach to optimizing and making it fast is cache all of the things all of the time, right? Use this capability of having warm environments, reusing containers for different invocations to cache things in global variables or local state or the file system, so you don't have to do initialization data every time. And what I wanted to cache was the model loading. When the model had been loaded once, I just wanted to cache it and reuse it without having to go through that process again. And this is what it kind of looked like, right? So I just used a global variable to control whether I loaded the model files and loaded the model, or I just returned the cached instance. And this is a nice way to kind of speed up model loading. And what that meant is that during what we call warm invocations, model loading is now essentially free. There's essentially no charge to do it because it's using that cached version. And this made quite a big impact on performance of those warm invocations. Now, I kind of made some headway at this point, but I thought there was further that I could go. And I was kind of thinking about the code and thinking about what it did. And I suddenly realized that when the classification function gets called, it gets called with 2 things, right? Your Twitter profile image, because it's your face to match against, and the tweet photo. But the Twitter profile image is going to be the same every single time. So the results of running face detection against it is going to be the same every single time. So why don't I take that kind of process out or cache the values somewhere, and then I can just reuse it from a local cache rather than having to go through this process every single time. Cut in half the amount of work it has to do in the image loading of face detection sections. And it turned out this was surprisingly easy because of how the face detection library worked. So the line at the top, model.allFaces, is what you call in the library with an input tensor to get array of faces that is detected in an image back, if there's any faces at all. And each face has a descriptor attribute. And the descriptor essentially is like the fingerprint for your face. And by comparing the different descriptors together, you can see how close they are. And if it's below a certain value, then it's a match, essentially. That's how you compare faces and images. And the descriptor is just an array of float values. It's 128 32-bit float values. And so what I can do is I can cache these values in Redis. So for your Twitter profile image, I ran this computation once. I just cached the values in Redis. And this had a really big impact on performance because it cut in half the amount of time I had to do in the image loading of face detection. Now it only has to do those steps for the new image from Twitter, not from your profile. It just uses those from the cache. So putting all of those together, right, had quite a significant impact on performance. You know, cold starts, apart from that first time you ever run it or you ever interact with the app, it's going to be down from 8 seconds to 6 seconds. And warm starts, it cuts by 50%, right? 5 seconds down to just 2.5 seconds. So by spending a little bit of time optimizing my application, I'd made some significant performance improvements. And with serverless, time is money. So for me, that would represent a direct saving on my bill from my cloud provider at the end of the month, right? And especially the warm starts, which is going to be most of the invocations, you know, I'd shaved 50% off by just using some simple optimization techniques. So at this point, I kind of done it. This was literally just a couple of weeks of me hacking around in the summer. I kind of validated that you could load the libraries, that you could read things from the file system and kind of interact with it and get it running on a serverless runtime. And then I kind of found that slightly nasty memory leak due to me not reading the documentation enough. And then finally, I'd actually got it working and made it fast and made it real time. Using those optimizations, the performance that you saw in that video when I clicked the button was the real performance of the application. It could process hundreds of tweets, hundreds of images in real time by just fanning them out, right? Using servers to scale them out horizontally to process them all in parallel. So to kind of sum up, right? You know, when I started this project, I really honestly had no idea that I would be able to do this, right? To be able to build myself a kind of an application to find unlabeled pictures of me on social media. And I'm not a machine learning engineer. I don't know data science or any of that kind of stuff. So But I gave myself a couple of weeks just to hack around. I'd heard about TensorFlow.js, and I started to see what I could do. And it turns out it works. It works really, really well. I think TensorFlow.js and Serverless work well because you can do machine learning classifications in parallel and actually maybe get more performance than having dedicated hardware. And I think Serverless is the future of the clouds, but I think TensorFlow.js is going to enable us to use machine learning natively within runtimes to do some really interesting stuff. And it's aimed at non-machine learning engineers, non-data scientists, and it means that even me, a kind of lowly developer advocate, can pick this stuff up and start to build some really interesting stuff. So thank you very much. I've got to be my good developer advocacy stuff here and say, this was all built on IBM Cloud Functions, which is based on a really nice open source project called Apache OpenWhisk, of which I'm a committer. So if you want a serverless platform that is based on open source rather than closed technology, go and check it out. And if you want any of the resources from this talk, I suggest you take a photo of this slide because you can get access to all the links on there. If you go to my blog, I've written loads of content about how I did this. The GitHub repo is at the bottom. If you go to developer.ibm.com, you can get these code patterns which show you how to put all of this stuff together really nicely. And then if you like OpenWhisk or Apache IBM Cloud Functions, you can go and sign up and start to use it and deploy it yourself. So thank you very much.
Thank you. That was amazing. The best part is we actually get to ask James a few questions because we still have time.
I'm on time. See, I'm on time. I told you. Oh. So I can't really see. Does anyone have any questions? If not, I have a question of my own. So I will give you a question that I normally get asked at the end of this presentation. That I have a slightly longer version that I cover as well, since we have a little bit of time left, is like, this is all great, but why didn't you use some kind of cloud API to do the facial detection, the face recognition, right? Why did you go through all this kind of hurdles to build this kind of neat thing when you could have used some kind of IBM Watson? And it's a really good question. And the reason that in this instance I chose to use TensorFlow is that most of the cloud APIs, of which IBM has one and Watson, that do face detection, if you want to do face recognition images, they require a training step, right? We have to upload sample images, and it'll train the model, and then you can start to do recognition. And I managed to find with TensorFlow this library, faceapi.js, that did pre-trained face recognition. So it could be real time. It didn't need you to upload photos and any of that kind of stuff. So, I think the availability of the pre-trained model was why I chose to use TensorFlow.js in this example and not try and use some cloud ML API. But there's some overlap sometimes between the capabilities of what both of these approaches can give you. And you need to think about what is most appropriate. If I'd had an API to use, I would have much rather used an API, much simpler, much cleaner. But TensorFlow has all these wonderful pre-trained models that actually mean you can do it within the JavaScript runtime, which may in some cases be even more performant than using some kind of cloud API service. But it's important to test out that kind of stuff.
So, no questions. Well, cool. That's because it was a beautiful and well-contained presentation.
All right, I'm around all day. Come and ask me anything. Cheers.
Yeah. Thank you.